Hi folks. So last time we were talking about DC motors. We talked about the principles of operation, but now we want to talk about implementation of DC motors. So in this class we're going to use an H-bridge driver, which is a nice way to drive a motor in two directions, because remember when we talked about motors in terms of operation, we said that if you reverse the voltage, then you'll reverse the direction of the motor. So that's kind of what we want to be able to do, is we want to be able to reverse the direction of the motor. So we're going to use, like I said, an H-bridge. We are going to, in particular, use the L298 package. This is not the only motor driver you can buy. There are many different types, but the L298 H-bridge is just a reliable older design that works just fine for our purposes, and conveniently I have a bunch of them in the lab. So it's an H-bridge, and you kind of draw in the legs here and it looks like an H, which is where we get the H-bridge from. So we'll be able to use PWM for driving it, so we can do our speed control by controlling the voltage, and we'll be able to control the direction by switching the transistors that are shown there. So here's what it looks like. This is a representation of the H-bridge. This is not exactly what's inside the chip. If you look at the lab or you look at the data sheet, you'll see that the inside of the chip is actually much more complicated. But this representation kind of gets the point across. So I've got 4 transistors shown. I've got, in this case, I'm showing them as BJT transistors instead of CMOS types, but it's just one way to represent this. So each of these is going to enable opening or closing this as a switch. So we can picture these as being switches that are going to be open or closed. We're not going to be operating in the amplification regime. Also included, we've got diodes. These are called flyback diodes. Or freewheeling diodes. These are going to be about protecting the transistors. We've talked about diodes before in that regard, but in this case they're about protecting the transistors, and so we've got one of them for each of the transistors. Now you'll notice C and D, those are my digital inputs. Not shown in here is any control over voltage, so I'm not including that in this particular drawing. So let's assume that C is high and D is low. So if C is high, then I'm going to be able to close the switches connected to C, so the upper left and the lower right, and I'm going to open the switches connected to D, lower left, upper right, and so that provides a path from the positive supply through the motor to ground. And so this particular path is going to be associated with a clockwise rotation of the motor. Now, if you reverse the direction on the leads, then maybe it's going to be counterclockwise, but again, for our example, we'll assume it's clockwise. Now what happens if we make C low and D high? Well, that is going to do the opposite thing, and it's going to give you the opposite path through the motor. And if the previous one was clockwise, then this one should be counterclockwise. So we're using C and D, our digital inputs in this case, to provide directionality to the motor. Notice that the supply has not changed, the ground has not changed, C and D are providing the direction. Now when you go to the actual 298 chip, it'll be a little more complicated, and we'll see that in the lab. Other fun things you could do something like a Darlington Pair here, where I've got 2 different transistors operating together. So the first one is a low power transistor that's connected directly to my computer. And then the second one is a high power transistor connected to the output, well, not really output, but output in regards to how we're using it, of the first transistor. So the first transistor will trip the second transistor, which will be your high power stage. So in this case, we can get a amplification that's relatively high. You can also buy them together in a single package, but this gets a relatively high amplification when you don't want to use switching the way we are in the H-bridge. So when you're driving these things, there's a couple different ways you could do them. We talked a little bit before about you can do current or voltage, current would give you torque and voltage would give you speed control. So here's an example of what we might have if we do voltage mode control, which is to say speed control. So the case here, we've got this chunk is our block diagram associated with our motor, and this should look familiar to you. We've got our electrical dynamics, we've got our mechanical dynamics, and then we've got our coupling, which is connecting the current to the torque and the speed back to the voltage. So that's all providing our motor model, and then we will apply to that some sort of amplifier that is going to take a commanded voltage and turn that into a specified voltage on the motor. So that is one way to do things. Alternatively, no, I forgot I had a slide here with some diagrams. So, sorry, we'll go through these first. So here are two schematics for ways you could do this, unipolar and bipolar. So notice in this case, both of them have a VM for what's going to the motor. This bipolar case, we've got a, let's call it a plus VDD and a minus VDD. So those are my supplies. Those are my positive and negative supplies. In terms of the, over here we've only got the single one. So we've got one supply on the unipolar case. We've got a command voltage in each of them and allows the output, the motor command voltage, to track. And so you can see that we're going to get a ratio here. So the motor voltage will be some scaled version of the command voltage. When you're looking at this bipolar case, notice that we've got this stacked arrangement of two transistors, sometimes called a totem pole. So in this case, we will see that as these things are switching, it'll allow current flow from plus VD or from minus VD through the motor and to ground. So now we'll jump to the current mode, and in the current mode, it's a little different. In the current mode, we are going to provide a commanded current, but we're not really going to provide a current at that point. We're going to provide a commanded voltage that is proportional to the current that we want, and so then we will need our current amplifier to run the motor, to measure the current through the motor, compare it against our commanded current, and that'll have a feedback operation. So now we will have a closed loop control essentially on current. So this should give us better dynamic performance, and our amplifier looks a little different. This portion should look really similar to what we already saw because that's the voltage control one. And then we're feeding into that this additional portion here where we've got our commanded voltage, which is again proportional to the current we want. We are comparing that against the current that's coming out. That's why we've got the sensing resistor over here. And so we're putting that together into our comparison here and feeding that to our bipolar amplifier like we had in the voltage case. And so in this case, we've got our current being R2 over R1 RS times our command voltage. So in terms of what this is going to look like, let's consider a PWM. So put in our diagrams here. So we've got a commanded voltage, which is the red one. We've got the triangle wave feeding in, which is the blue one. So this is just a generated triangle wave. And then we'll run this through a comparator, and the output of that is going to be our PWM. That is going to be passed through the totem pole here that we saw previously. And then notice we have, again, just like before, the flyback diodes that protect our transistors. And so in this particular case, we're switching things on and off instead of running these as the previous cases where they're in terms of amplification. So we've got our PWM going there. You can see your PWM is here. We've got our commanded signal in red. Yep, there we go, PWM. And if we wanted to, we could also have a triangle wave generator, so we could build this up. Now we're not really going to build this up ourselves. We're going to use the built-in PWM functions in the Arduino. But if we were going to build this up ourselves, you could do it out of a couple of 741s. And so in terms of the 741s, we would have our square wave generated, and then we would run the square wave through an integrator, and that would give us our triangle wave. So we could do this all in circuit if we want. Certainly somebody's doing this under the hood in terms of the Arduino. Yeah, you already know what those are. So here is our PWM that is the response to that red commanded voltage. And so your overall amplifier might look something like this, where you've got the commanded current. In the current mode, your overall might look something like this, where the commanded current, you can see over here we've got that sensing resistor so that we're still getting our current measurement coming back through, and then this part is all going to look the same as what we were just dealing with. Okay, so we've got voltage, we've got current control. We could do either one of these. So another implementation issue we need to think about is gearing. So for those of you with a mechanical background, this seems pretty obvious. But when you are thinking about your motor, you're going to be able to buy a motor that is capable of a particular speed and a particular torque. And certainly it's going to have a curve. It's not just a specific value, but you'll get a maximum torque and a maximum speed. Very rarely are you going to get the absolute right torque and speed combination for your application, and so you're going to have to consider a gearbox in order to convert it to what you want. So remember when we were talking about the design of a motor, we were talking about how to get higher torque. Basically the physical parameters of the motor had to go up. It had to get much bigger. So if you want to get more torque out, you might want to buy one that has higher speed and then gear it for torque. So that's one way to go about it. Now when you choose a gearbox, you got a couple of choices. You could choose Spur Gears or Planetary Gears, and sometimes again this is based on just what the manufacturer has on offer. But if you want to design your own gearbox, you'll have to choose how you want to do this. In terms of Spur or Planetary Gears, you need to choose the material. So your cheap ones are going to be plastic, but are they going to last? Not quite the same. You have to figure out which is the appropriate one. So in case you don't remember these things, this is what a Planetary Gear Set looks like. Notice that your output shaft is directly in line with the input shaft because it's going through this planetary system. The planetary system has that sun in the middle, and it's got the planets going around it, and it's got an outer ring. And so all of that's moving together. Alternatively, you might have Spur Gears, which is your more typical arrangement that I think of for these sorts of things, where the output shaft is often offset from the input shaft. And so you'll see something like this one that's in the lower right, where you can see the output shaft is definitely off-center. Again, you're often just buying these, so you have to choose. Now, when you buy from, say, Pololo, they've got one particular motor, and they've got a bunch of different gear heads, and you can specify which gear head you want for your application. Another thing you might see is worm gears. So worm gears, you've got this sort of operation where you can see that the output shaft is turned 90 degrees from the input shaft. The nice thing about worm gears is that they're not backdrivable. So if you apply a load to the output shaft, it doesn't turn the input shaft. Is that the right choice? Not always. It depends what you're doing. So I think of robotic arms as being a good case. When you have a robotic arm and you want to drive it through some particular trajectory, do you want the user to be able to push the output of the robotic arm, the end effector? Do you want it to be able to push the end effector and move it around or not? If you want it to be able to move around, you probably don't want worm gears. If you'd like it to always be driven by the motors and never by the end effector, then worm gears might not be a bad idea in order to make sure that it's not backdrivable. So when we are thinking about how this motor is going to work when it has a load on it, you have to consider what's going to happen in terms of the reflected inertia. So the inertia that the motor is going to be seeing is the total inertia that combines the rotor inertia with the load inertia. So you need to be able to consider this and design your gearbox appropriately. And so how do you maximize, well, I suppose, let me rephrase that. When you think about your gearbox, there are design parameters you can choose. One way that you can do it is you can maximize power. So if we wanted to maximize power, which is not the only way that you want to do it, but if you wanted to maximize power, you could go through this process. You could calculate the kinetic energy, and this depends on the load. You could figure out the power from the kinetic energy, so it's going to be a differentiation of the kinetic energy. You could then figure out what is the power at the motor based on the power at the load. And you could then take your acceleration based on your torque and your load inertia and assume that your acceleration is constant. And so you'll get your power at the load like this, and then we can maximize it by differentiating, and we'd end up with our gear ratio being specified as depending on the load inertia and the motor inertia. So if we know what those both are, we can calculate an appropriate gear ratio that would maximize power transmission. Is this the only way to do it? Absolutely not. This is one way to do things. Certainly this part is the sort of thing that you would do in a machine design class, but you do need to be considering those sorts of things when you're choosing a motor. All right, so other things that you might run into. You might run into linear motors. I don't think I've ever seen these in a good application. I've seen examples of them, but you'll have to tell me if you've got a great application for a linear motor. It's like taking a DC motor and unrolling it. So we've got our guide is linear instead of being rotary, and so we've got the brushes and the commutation going on linearly. So it should have been unwrapped, not unwarp. The problem with that is that now, because it's unwrapped, you have physical limitations, and you need to be able to deal with the fact that you don't have a gearbox and you don't have stiffness in the same way. But I'm sure there's good applications in terms of the smoother motion. You might also deal with brushless motors. We do see these a lot these days. So brushless motors, instead of having the commutation provided by these brushes, which, that's the brushless part, we know that the brushes tend to fail, and so could we do this a different way? So in this example, you can see that we've got a magnet that's spinning that's over here. We've got a magnet that's spinning that's got an element, a portion of it that is not magnetic. And so as it's spinning, we've got these Hall effect sensors, and the Hall effect sensors are linked to transistors, and so as it's spinning, that controls which transistors are enabled, and that controls which direction the current is going to flow. And so you can see that we get this pattern that's on the right, that as a function of rotation angle, the current is either flowing or not flowing. And so as we switch through these different combinations of the current flowing through the different paths, that's how we're going to get our torque. Now, you don't always have this sort of system that's driven by a magnet and Hall effect sensors. Here's a nice picture of one. Notice that this one is a little different design. Previously, we were looking at the rotating part as having the coils, and the stationary part as having the permanent magnets. In this case, it's reversed, and so inside is the stator, and that's got the coils, and outside is the permanent magnets, and that's the rotor actually. And so in this case, it's like I said, it's a little reverse from what we're dealing with, but that enables you to switch the current flow through the coils and not worry about getting the current through from a stationary to a rotating object. So obviously that's going to free up some complexity in terms of failure mechanisms. But what happens, as I started to say, is when you don't have the Hall effect sensors, because sometimes you want to save money, so you take out the Hall effect sensors, you take out the transistors, you want to switch it a different way. And so when you see like a hobby RC motor, it's got a little amplifier box, and that little box is doing some sort of algorithm to estimate what it should be. Does it work? Absolutely. There are other problems associated with it. So we do have less maintenance and less noise and higher voltages because you don't have the brushes, and the brushes are where the failures happen. But you do have the additional cost of the additional electronics, and you can end up with higher torque ripple. So it's not always a perfect solution, but you do see brushless DC motors a fair amount. So I am going to stop with that. Our last part of the actuator section will be stepper motors, so we'll jump over to stepper motors next.